Hello, everybody. So what we're looking at today is going to be section 5.3 in your book. This is double integrals over polar coordinates. Um, yeah. So I know I always say this and I'm always wrong, but I think this topic's going to be easier than the previous topic. And the reason I think it's true today is because um, I feel like I looked over the integrals and they look like easier integrals for the most part. And this section doesn't have a lot of stuff in it. So I think it'll be okay. You know, if I'm wrong, it'll be another 2 hour lecture. If I'm right, it won't be. We'll find out. Okay. So what were we going to do in this section? Well, we're going to learn to recognize the format of a double integral over a polar rectangle, which we haven't defined yet, but we are going to. And we are going to evaluate double integrals in polar coordinates. And we are going to use double integrals to compute area and volume. So basically, all we're really going to be doing in this section is we're just learning how to do these things that we've already been doing in rectangular coordinates, but now with polar coordinates. And I don't think it's that bad here. So let's go ahead and get started. So let's just look at this. So this is just kind of an introduction here, intro. Um, so we know that when we did double integrals for um, Cartesian coordinates, we had a certain type of shape in the xy plane, right? So what I mean by that is um, you were, oops, right? You had like a little box in the XY plane, and then you extended that up. That's a bad place to put that. Hold on, I'm gonna move that where it's not in the way of the axis. So, right, you were calculating the volume of little boxes like this, right? So for double integrals of Cartesian, I should say in Cartesian coordinates, um, we added up the volume of boxes like the one shown. Right? And the base of the box was a little rectangle. So the base, when I say base, I mean just the little rectangle down there. Each box is a little rectangle with dimensions delta x by delta y, right? And I mean, probably you can just remember that. We're not doing much with it, by the way. I mean, I'm just saying it's just kind of for reference here. So, like, if I make a little box here, right? Oops, sure. So if I just do these, you had a bunch of boxes like so, and then each box had a width and a height there of delta x by delta y. Okay. Now, when we're in polar coordinates, this isn't the shape we're going to get. So in polar, it's a little different. Okay. Um, because we're going to have a delta theta and a delta r, right? Because we'll be dealing with r and theta. Delta r and delta theta, because those are our variables instead of x and y. Um, r and theta and not x and y. So that's a pretty simple idea, right? The fact that we have different variables, so we have different variables. But when you look at what happens in the XY plane, you start to realize that's a little bit of an issue. Not an issue, but there's some thinking that we have to do, right? Because you have rays coming out of the origin if we're dealing with um, polar coordinates, and then your delta theta, need a thinner line here. I need to be able to write a line. You have a delta theta that's measuring some kind of delta for the theta, and then you have some kind of delta r, and your delta r will be like that. And so what happens is the actual, that's not very well drawn, but is you have this kind of shape here instead of just a little rectangle like you do in the shape up there, right? So you have a shape like that. So the base of the rectangle does not have straight sides, right? Two of the sides are curved. Non-straight. Curved. That's called curved. Curved sides. Right? So specifically when I'm talking about the curved sides, right? This one right here, that's curved, and that's curved. Okay, so these are just a little bit curved there, and then these two are straight, but they're not parallel. So that's the kind of thing that we have to somehow calculate the volume, no, not volume, the area of, because, so the dA used to be dA equals simply, well, like I could say like delta A first, I should say. The delta A used to be delta A equals delta X delta Y. And then that turns into dA equals dx dy when you look at it in the integral. But here it's a little bit more complicated. And specifically, one thing that's an issue is that the further you go out from the origin, something interesting happens. So let me try to draw it. Okay, so I'm trying to draw that kind of a long shape here. So you can have, so you have a delta theta, okay? Right there, right? That's a delta theta. Now the thing is that's the same delta theta over this entire section here. And so if you have a delta r down here, right, you have a little area. And if you have a delta r over here, you have a little area. But I mean, probably you can see that the further you are away from the origin, the bigger the little area is, right? So you can see, hope you can see, that the further you are from the origin, the larger the area will be, even with the same delta r and delta theta, right? Like I tried to draw these so this distance was about the same as this distance, and here the angle here and the angle here are the same angles, right? It's just that the further away you go, if this is like 3 degrees, 3 degrees is a big difference out here compared to right here, even though the angle itself is the same angle. And so the thing is that what you have to do is you have to basically figure out how to, you basically have to figure out how to estimate this length here. And so that's what it comes down to, is that when you draw this for, I guess, the third time now, but this will probably, I was going to say it's going to be the last time, but I mean, it's probably not, let's be honest. When you have a shape like this, if you've got a distance here, r, and then this is, delta theta, and then this right here is delta r, then it turns out that this side here has length r d theta. No, not r d theta, r delta theta. Okay. And so the bigger r is, right? Because I put r here, like measuring this distance. So the bigger r is, the bigger this will be. So like the bigger r is, the bigger this will be. And so this distance actually depends on this distance. That's where I'm getting at. And so what we do is we say if delta r is small enough, if delta theta and delta r are small enough, for whatever small enough is, I'm not going to explain that, then your shape like this, the sides are still curved, but if the angle's small, then this and this are almost the same length, right? This is shorter than this, right? This is longer, this is shorter. But if the delta r is small and this is also small, then these are about the same length and these are the same length. And so you've got a shape like this where this is approximately r delta r. This side is approximately r delta r. This side is, oh, sorry, I keep saying delta r, delta theta. R delta theta and r delta theta. And then this side and this side are just the delta r and the delta r. And so if that's the case, it's not an exact value, but you can say because of this, the delta A, the area of one of these little things, is going to be approximately, if you treat it as if it was a rectangle, it's not a rectangle, right? Because the sides are curved and these are not parallel. But if it's basically a rectangle, and if it's basically a rectangle, its area is going to be length times width. I just erased it. Like length times width, right? So this times this. So it would be r delta theta delta r. Okay? And then what this does then in your double integral is this. So the punchline when you set up a double integral in polar coordinates, your double integral over d of f of r theta, we'll do r theta dA, is actually going to be a double integral over d of f of r theta. And your dA is r dr d theta. And you've got this extra r here, right? Okay. And the reason for that is, basically what we just drew here. When you're in Cartesian coordinates, you have a little box like this, and it's delta x by delta y. But when you're in polar coordinates, you have little boxes like this, and they are delta r and r delta theta. So basically, this has an extra r compared to this. And so that shows up in your integral as part of the dA. Okay, so that's the first thing, right? So first thing we need to know. Okay, so we know that. Let me look and see if they cite it as a theorem. Yes. So this is their definition. The double integral of f of r theta over the polar rectangle, which I'll explain in a minute. Polar rectangle r in the r theta plane is defined as, so double integral over r f of r theta I'll just write dA, and then they go, it's limit m and n go to infinity, sum, I goes from 1 to m, j goes from 1 to n, f of r ij theta ij delta a. And then they rewrite the same thing, but then they replace the dA with what it is. So this is their definition. I'm just writing it down kind of for completion here. And then the delta A is r delta theta. Okay. So yeah. So let's actually do something now. So what do we want to do? So a polar rectangle, let's define that. Is the set of all points let's see, satisfying. So it'd be like, I guess R for rectangle, call it R for rectangle. The set of all R theta such that, and we're just going to have this. You just have theta between A and B, R between C and D. Right? So this looks like a rectangle. And if these were X's and Y's, this would be a rectangle. And so we call it a polar rectangle if it's in polar coordinates. And it is what we already have drawn several of them, because this kind of shape is a polar rectangle, right? So like, for example, if this line right here could be like r equals 1, and this line right here could be r equals 2. And then we have angles. So like this angle could be like 40 degrees, but well, let's just call it 30. We're going to pretend. Like that could be pi over 6, and this could be pi over 3, right? So you see that we have constants to get you that shape. So this would be r equals the set of all points r theta such that, and then you just say theta is in between pi over 6 and pi over 3, and the r is in between 1 and 2. right? So it's not a rectangle, but r and theta are between constants. Okay, so that's just a sample polar rectangle. Okay, so that's what we're talking about is regions like that. And then what they do is they say, um, so you compute to compute a double integral over a polar rectangle. And they use, this is the rectangle here, r equals set of r theta, such that, and they've got, I guess it doesn't matter what order I do it. They have r between a and b is what they're using for r. And for theta, they are using alpha and beta, it looks like. Doesn't matter what variables they use. But to compute a double integral over a polar rectangle like that, the double integral over r of f of r theta dA, you would have two choices here. You would either do an integral from r goes from a to b, theta goes from alpha to beta, and then it would be like f of r theta, and then they go r d r d theta, like that. Or, right, you can always change the order. You know how these work. Um, duplicate. So you could change the order here. You can go from r goes from a to b there, and theta could go from alpha to beta. And you could do the theta integral first and then the r integral. So all depends on which way you want to do it. There you go. So another thing they write is for conversions from rectangle to polar. Or to change from Cartesian to polar. So if you had a double integral over r of f of x, y, dA, right? So if it's an x and y, what you need to do is you would need to replace the x with r cosine theta. You would replace the y with r sine theta, and then the dA would be r dr d theta. And again, part of doing this right is just not forgetting about this extra r that's there. Okay, so that's kind of enough integral or enough intro. We're ready to do like integrals, but before we do that, I just want to the homework might start out with just like describing regions or something, and so let's just see if we can do that. So I'm going to just leave this homework here and come back. Preview. Okay. Yeah. So like the book starts out, sorry, the homework starts out pretty simple. So they give you, I don't have this kind of graph paper here, so I'm going to have to do my best. But Okay, that's good enough. I'm just gonna label this, like pretend that this is 1, 2, 3, 4, like that. And then they're labeling some angles on here like this. They'll go like maybe they do like this. Okay, and they'll tell you the angles here. Like they say, I have to think about what this would be. That's probably like 30 degrees past. So pi 7 pi over 6, maybe. So like let's say that's 7 pi over 6, and then let's say that this right here is going to be 5 pi over 4. Okay, and then so they give you something like this, and then what the question is, they say express d in, so d is the region, in polar coordinates. And then they give you like d equals, and it's just the way that I was writing it, right? So d equals r theta, and then they go r in between box, box, and then I didn't leave enough room, so let me move this over. And then they have theta in between box, box, right? And you're just filling in the boxes. And there's really not that much that you have to do here. You just have to take note of the numbers, right? So like I called this 1, if you can read it. 1, 2, 3, 4. So this shaded region is in between 2 and 3, right? Um, so in between 2 and 3. So you just go, okay, well, that's easy. 2 and 3 then for R. And then for theta, well, actually they just listed them, so you just have to write those in. So that was 7 pi over 6 to 5 pi over 4. And so that's how they start out on the homework, just kind of getting used to this. So that's a polar rectangle. Um, and it's those are should be super fast to do. Um, they have some dumb ones. So I saw that I unfortunately I can't make it give me a dumb one right now, but I'll try to explain what the dumb one said. Um, so here's another example that says express d in polar coordinates. And they say where d is the part of the disk, or a disk actually, of radius 16, centered at the origin, lying to the left of the y-axis. And I don't really like this kind of question here. Another one, like I don't know how this one's going to be. We're going to try it and see. But I saw one of these questions said it was exactly the same as this, but it said lying above the x-axis, and that made no sense. Like these don't really, like the wording doesn't make a lot of sense here. So you may have to just like do one and get it wrong, and then figure out how to do it from there. So let's think about this. So I mean, of course, we're talking 3 dimensions, right? Where you got x, y, but we can look at it just in the xy plane here. So you have x and y like that. And so what are we looking at? So the part of a disk of radius 16 centered at the origin. Okay, so I can draw a disk like a circle, right? The disk is the inside as well. So this is 16. So we got this disk radius 16. Okay, that's not what we want. It says lying to the left of the y-axis. Okay, that's actually not that bad, right? Lying to the left of the y-axis, that would actually just be here, right? So figuring out what they mean there is kind of the hard part. And then you say, okay, well, that's the part of the disk that's lying to the left of the y-axis. So how would we describe that? So d set of r theta such that we need minimum and maximum radius again. And we also need minimum and maximum theta values. Okay. And so let's do the radius first. So first of all, remember like on one like this, right? You got radius 0, radius 1, radius 2, radius 3, and that was radius 2 to 3, right? If you had filled this in, right? If you filled this in like this, what that would have done is it would have changed this to a 0, right? Because it's all going all the way to r equals 0. And that's no different than what we're looking at down here, right? It does start like there's no hole in the middle. If there was like a hole right here where this was not included, then, you know, wherever this was, like if that's a 1, you would start at 1. But there's no hole in the middle. So if there's no hole in the middle, then this is definitely going to start at 0. Okay. Now for the maximum radius, obviously this goes all the way out to a radius of 16. So that's 0 to 16. Okay. So that's the first part. Then what you need to do is you need to figure out the angles. Well, you need to be, you know, comfortable with the unit circle. You know, look up a unit circle if you need one. Right? If you Google unit circle, you'll find one. But we're measuring angles in standard position, right? So if I put a vertical line here, right, what's that? What's this angle? That's 90 degrees, right? So that's pi over 2. And then what's this angle? Well, that's all the way around to here. That's 3 pi over 2, right? So that's it. Pi over 2 to 3 pi over 2. So you've got to be at least comfortable enough with the unit circle that you can read angles like this off there. And you need to draw this region. Otherwise, you know, you may not understand their verbal instructions. Well, written, not verbal, but you may not understand their written instructions as to what the region is. So you start out with a few of those. And then once you get far enough, then you actually are going to start doing some integrals now. So let's do some integrals. So some integrals are pretty simple. This is straight off the homework. I'm literally doing a homework question now. So this is going to be example integrals. Actually, this says set up, but do not evaluate it, but we're going to evaluate it. So I'm going to evaluate the double integral over r of f of r theta dA over r equals r theta such that 7 less than r less than 8, 3/4 pi less than theta less than 5 pi over 3, where f of r theta is 8r. Okay, I'm looking around for my calculator because we're going to need it momentarily. It's across the room, of course. Where else would it be? All right, got it. So let's set up the integral, right? So let's just set up the integral. It should be pretty straightforward here. So you're going to have a double integral, leaving some space, the function that we're integrating is 8r, okay? And then your dA, remember your dA is r dr d theta, right? Don't forget the extra r, okay? R dr d theta. Now, once you have that, then you have your limits of integration. Well, because this is a polar rectangle, the limits of integration are very simple. So we're doing the r integral first, just because that's how I wrote it. R goes from 7 to 8. So 7 to 8. And then you do your theta integral. Theta goes from 3 pi over 4 to 5 pi over 3. Okay, so there's your integral. So now let's evaluate it. Once you set up the integral, you're not actually, like once the integral is set up, you're going to actually do the integral the way you've been doing double integrals. And that's why this is not so hard here. So first thing to do is you have this extra r, but once you have the extra r, you do combine it with whatever else is there, right? So you have an 8 and an r and an r, that's 8r squared, dr d theta. So don't feel like it's not separate. Like once you add that extra r, you actually, put it with the rest of the integral. So combine with, the rest of the integrand. Okay, so there's your integral, and this is the integral we're going to do, and it's not harder than other integrals. I mean, the hardest part is that you have to keep writing pi, right? All right, what's the antiderivative of 8r squared, right? Because we're doing the r integral first. So it's going to be 8r cubed over 3, and we're going from 8 to 7. And then we got a d theta. So you have integral 3 pi over 4, 5 pi over 3. Here we have 8 cubed over 3 minus 8, 7 cubed over 3 d theta. So you punch that into a calculator. Numbers are going to be big, right? 8 times 8 to the 3 over 3. And then minus 8 times 7 to the 3 over 3. And when I do that, I get 3 pi over 4, 5 pi over 3. And that works out just to 1352 over 3 d theta, provided I didn't make a mistake. Now, this is actually a really easy integral too, because you can take that constant out front if you want to, right? Because you have rules for integrals. And something that happens a lot in these is you end up integrating just d theta. And thing about d theta is that the antiderivative of d theta is just theta. And then you go 3 pi over 4 to 5 pi over 3. And it's just going to be 5 pi over 3 minus 3 pi over 4. So I'm going to punch that into a calculator as well. 5 times pi over 3 minus 3 times pi over 4. That's 11 pi over 12. I'm going to multiply that by 1352 over 3. And I get 3718 over 9 pi. And it's just a number. Okay, so that's it. We did our first integral over a rectangle, polar rectangle. So not much of a problem there. Okay, so if they are over polar rectangles and your function is pretty simple, that will work out okay. Let's do another one. Evaluate, double integral over r f of r theta dA. They say r is going to be r theta such that, okay, 7 less than r less than 8, 5 pi over 4 less than theta less than 7 pi over 4. Okay, the bounds are different. And then our function, f of r theta, is 4r squared sine theta cosine theta. Okay, so, this is going to be a slightly more involved integral to do. You have your f of r theta, that's 4r squared sine theta cosine theta. And then you have your dA. dA is r dr d theta. You don't forget the extra r. And then r is going from 7 to 8. And then we got 5 pi over 4 to 7 pi over 4. And so this is our integral. So first thing to do is going to be to combine this r with the other r's, right? So you actually have 4r cubed sine theta cosine theta dr d theta. So a lot of times, I'm not going to say it's not going to matter on this one, but on a lot of problems, like you might need integration by parts or substitution or something, like some advanced technique. And if you forget the r, a lot of times you're going to make your integral impossible because they expected you to do it right, obviously. And if you missed out that part, you just make the problem impossible to solve. It's not just that you get a wrong answer, it's just actually impossible. All right, and anyway, I wasn't done writing this. That was from 7 to 8 as well. Okay, so we're actually going to do this integral. We're going to do our first antiderivative here. So we're integrating with respect to r, and here's our r's. So what's the antiderivative of 4r squared dr? Right? We're doing power rule, so r to the 4th over 4. And then the sine theta, cosine theta are just along for the ride. You got your d theta, and this is from 7 to 8. Once you get to this point, of course, the 4's are going to cancel. So we have integral 5 pi over 4, 7 pi over 4. We are plugging in the 8 and the 7, so you have 8 to the 4th sine theta cosine theta minus 7 to the 4th sine theta cosine theta. I could have moved the sine theta cosine theta out, so I wouldn't have had to write it twice, but I didn't. So we've got 8 to the 4th minus 7 to the 4th, which turns out to be 1695. So 1695 sine theta cosine theta d theta. So actually this is one where you would technically need a u substitution. So your u substitution would tell you that u should be sine theta, du should be cosine theta d theta. And then my integral, I'll put the 1695 out here, is going to be u du. And if you want to be good and do this in a smart way, you can translate your limit. You can go, the top limit was theta equals 7 pi over 4, right? But if you take that 7 pi over 4 for theta and you plug it into your substitution, you would find out that u should be sine of 7 pi over 4, which, I mean, you can use a calculator, but 7 pi over 4 is like all the way around there. And it's a 45-degree angle in this quadrant. And the y value is negative. And so it's going to be negative square root 2 over 2. You could use a calculator for it. But you could use that as your top limit. And then you never have to go back to theta. Now your bottom limit, same thing, theta was 5 pi over 4. So u would be sine 5 pi over 4, which is down here, sine of 5 pi over 4. It's a 45-degree angle in this quadrant, and also the y value is negative. It's also going to be negative square root 2 over 2, which what's going to happen there? So you can do this integral, you can finish this out, but if you translate the limits like this, what you can realize is that once you end up with the same limit on the top and the bottom, your integral is going to be 0. So recall, any integral from a to a of anything is just automatically 0 when the top limit and the bottom limit are the same. So I don't have to even finish this. That answer is 0. And I will usually do this for, I'll usually do this when I have sines and cosines. If you, like, I'll translate the limits, because a lot of times it's not unusual that for a substitution involving a sine or a cosine that your limits turn out to be the same after you translate them, and then as soon as that happens, you know your integral is 0. But anyway, we could have finished that integral the normal way. Do they? Oh, that's funny. They actually used the opposite. They used cosine for your u, so they wouldn't come up the same there. They still got 0, of course. Okay, so that's how those integrals work when you're just in polar rectangles, okay? But you're not always going to have polar rectangles, right? You can have more complicated shapes. So you could have a general polar region, right? So not every shape is a polar rectangle, okay? A more general situation is this. So we're looking in the plane, and we're still going to want constants for theta, right? So like this could be theta equals alpha, and this could be theta equals beta. Those were what we were using before. But instead of having just this kind of constant radius and this kind of constant radius, we're going to allow those to be functions. So you could have, just a squiggle there, and that would be r equals, I don't know what they call it. I'm just going to call it r2 of theta. And then on the inside, you could have a different function, and that could be r equals r1 of theta. And then the region that we're talking about, of course, is the one in between there. Right? That could be a region. And so for that kind of region, the domain, I shouldn't have called it R. Hold on, let me change. Come on. No, go forward. Oh, I can't go forward. Once you go back. Okay. Color it in again. This time, write a D. So that kind of domain there would be the set of all r theta again, such that the way we did this, r is going to be between r1, which is a function of theta, and r2, which is a function of theta. And then your theta is simply going to be between two constants. Okay. And so if we do that kind of thing, then your double integral would be like this. Uh, and a double integral over d would be double integral. You would have to do the r integral first, which we've been doing, but r equals r1 of theta to r equals r2 of theta of your function, whatever that is, r dr d theta. And then your theta would be alpha and beta. So just like for Cartesian double integrals, you can have functions here for r, and then constants here. So that's it's not nothing unusual, but we have that, and because of that, you're often going to have to translate regions from x and y to r and theta. So that'll be the harder part there. So we'll have to move between polar or Cartesian and polar coordinates. All right, so how are you going to do that? So you want to recall from the section on polar coordinates that we had that our conversions were x was our cosine theta, y was our sine theta. Yeah. Uh, y over x was tan inverse, no, tan theta, which you don't use very much, right? And then also x squared plus y squared equals r squared. Okay, so you're probably not going to use that bottom one. You're just going to stick to the x and the y and the r conversions. Okay, so let's try to do this. Express the region d equals, and we're going to go, it's x and y such that 4x squared plus 4y squared less than or equal to 28 in polar coordinates. Okay, so how would you do that? Well, start with the inequality, right? So start with that inequality. Like 4x squared plus 4y squared less than or equal to 28. You want to try to first find any x squares and y squareds that you can turn into r's, and then look for just individual x's and y's first. So that's just advice here. Advice. 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 Okay. So look for x squared plus y squared first, so you can use x squared plus y squared equals r squared. Then you can go use the x equals r cosine theta and y equals r sine theta. Okay, so that's just comments here. So like when I see this 4x squared plus 4y squared, I know that you could factor out the 4 and have x squared plus y squared less than 28. You could divide both sides by 4 and have x squared plus y squared less than or equal to 7. And then, of course, x squared plus y squared is going to be r squared less than 7. Okay? And then if you square root this, r is going to be less than or equal to square root 7. And there is a comment here. Technically, uh, the square root of like a squared is absolute value a, but r by convention is going to be positive. So absolute value of r is just r because it's already positive. So what I'm saying is you do not need absolute values on that. You can just not. Okay? So you end up with this. So this is just r less than or equal to 7. So really we're already done. We can write it. So what you would do is like on the plane, what is this? Right? If r is less than square root 7, that means that square root 7 is the radius. And you just have that, the inside, right? That's where the radius is going to be less than square root 7. And that's your domain. Okay, so what is it? Well, we have this restriction here, right? So what you would do is the domain is the set of all r theta such that, of course, you have r less than or equal to square root 7, but remember that r is greater than 0, so you can just add that in yourself, r greater than 0. And then for the theta, if you don't have any restrictions on theta, it's just going to be all the way around a circle. Okay, so since we didn't have a restriction on theta, you just go the full circle, 0 to 360 degrees, 0 to 2 pi. So theta is not restricted. We just use 0 to 2 pi. And I guess technically it doesn't matter if that's in there because there's no, but I'll take it off. So there you go. So that's our first example of that, right? So the key was, again, try to look for x squared plus y squareds that you can do first, and then think about more complicated things. All right. Oh, okay, here, yeah. So here's a slightly more complicated one. Again, express in polar. D equals set of all x and y such that 7x squared plus 7y squared looks familiar, right? But this time less than 77x. Dun dun dun. What's the x do? So the strategy's the same, right? Same strategy. Same strategy. So we're going to write out our inequality that we got. 7x squared plus 7y squared less than or equal to 77x. So you can factor out a 7. Or, I mean, if you're comfortable 7x squared plus 7y squared, if you want to just go 7r squared, that's fine as long as you're comfortable doing that, of course. But, I'll factor out the 7. Maybe. Like that. I'll divide both sides by 7. Get there. Now, again, remember, look for do x squared plus y squared equals r squared first, usually. It's just usually good advice here. R squared less than or equal to 11x. Okay. But that doesn't take care of all your x's, right? So the next thing you want to do is now use x is r cosine theta. So you have r squared less than or equal to 11 r cosine theta. Okay. Um, Now, at this point, you have a couple of things you can do here. Uh, it's not uncommon to have this situation where you have an R on both sides like this. And what you can do is, you're not allowed to divide by zero, but R is generally not zero, right? The only point where R equals zero is the point 0, 0. So what you would do here is you would just say, like, okay, um, so we're just gonna say, well, R is only zero. Oh, R is only zero at, I'm gonna write it. R is only zero at point 0, 0. Okay. So for the rest of the plane, R is not zero. So usually R is not zero, and you can just divide by zero. Sorry, divide by R, which is not zero. You can divide by R. Additionally, if we divide both sides by r, we don't have to worry about the symbol flipping to the other direction, right? Because when you divide by a number, an inequality switches. You don't have to worry about that because remember, by convention, r is positive. So also, dividing by r does not flip the symbol to the other symbol because by convention, r is positive or zero. R is not negative by convention. Okay, so if we do that, so you have r squared less than 11 r cosine theta. So you simply divide both sides by r now. R. We end up with r less than or equal to 11 cosine theta. Okay, so at that point, you can say that d is going to be equal to, we're not done, but we're partially done, such that the r is going to be between 11 cosine theta. That's what we just figured out, right? And also greater than or equal to 0. R is allowed to be 0. We were not supposed to divide by 0, but r is allowed to be 0. And then what about theta, though? And there's a small amount of work that we still have to do to get theta. Kind of sneaky here. It's easy to miss. So the theta is a little tricky. So here's a trick, right? So you're going to see the trick now, and then you'll remember it for the homework because you're all going to watch this lecture. I guess the people who aren't going to watch the lecture aren't going to know what they missed. So here's the thing. Like, take a look at this. You could look at the original one, but I'm going to look at the one that I circled here. So look at x squared plus y squared, and it was less than or equal to 11x. Right? Now, think about this for a second. The left-hand side there is x squared plus y squared. Isn't that positive guaranteed to be positive? Right? Since x squared plus y squared is guaranteed to be greater than or equal to 0, must be greater than or equal to 0, then the 11x, which is bigger, must also be greater than or equal to 0, right? So, which is bigger, the 11x, which is bigger, according to the inequality we have, must also be. So stop and think about that for a second. So because this is positive or zero, this must be positive or zero, which means that x must be positive or zero. So x must be greater than or equal to zero, right? But x is arc cosine theta. So arc cosine theta must be greater than or equal to zero. But r is positive. Since r is positive, the cosine itself must be greater than or equal to zero. So hopefully you follow this logic, right? It's just a bunch of this is positive, so this is positive, so this is positive, right? X squared plus y squared is positive, so 11x is positive. 11x is positive, so x is positive. But x is arc cosine theta, so arc cosine theta is positive. But if arc cosine theta is positive, cosine theta must be positive, right? Because the r is positive. So a positive times a positive would give you a positive. Cosine theta can't be negative, or this would be negative. So the cosine must be positive. And the whole point of it was to get to that point, because the fact that the cosine is positive, you can say, here's the punchline here, for what theta is cosine theta positive, right? You need a unit circle, right? You got a unit circle there. You have a unit circle, you know that you have 0, pi over 2, pi, 3 pi over 2, and then, back to 2 pi. The cosine of theta is positive in this section, right? No. Cosine theta is positive this section when the x is positive, right? In that section. So the way they decided to call that is they said this section right here, from the 0, this is down to negative pi over 2, and then this is up to positive pi over 2. That's the section that they used. You wouldn't want to use, like, you wouldn't want to say, like, call it 3 pi over 2, because 3 pi over 2 to doesn't go to 0. It's 3 pi over 2 to 2 pi, and then it would be past 2 pi. So you'd have to use 3 pi over 2 up to 3 pi over 2 to 5 pi over 2 or something. You wouldn't want to. So instead of going from here to here, like all the way around the circle, and then from here to here, they just say from 0, just down negative pi over 2 and up pi over 2. And that's how they chose to list it. I guess it shouldn't make a difference. But the point is that's where the cosine's positive. So once you figure that out, you can go in here, and that's where you get these numbers. And I understand that that's tricky, but we just did it. So since we did it here in lecture, you should be able to do it on the homework, since it's the same question on the homework. Okay. Let's see about doing an integral. Yeah. Let's do another integral. That's another, I don't want to do that one. It's too easy. I want a non-polar rectangular region. That's a polar rectangular region. Give me a harder integral, computer. Don't give me confetti. Let me move on to the next question. Ha. Okay. Example. Oh, set up but do not evaluate. We'll try to evaluate it, and if it's too hard, we won't do it. But the reason I am writing it out is because no, it's still another one. Okay, you know what? Okay, this is not a this is still a polar rectangular region, but it's a different type of question. So we'll do it. So they say set up double integral over r of negative x squared minus y squared plus 9 dA in polar coordinates, where r is xy. So they're giving it in xy, but we're going to have to write it in polar. 3 less than x squared plus y squared less than or equal to 7. Okay, that's it. Right? So, like, what would you do here? Okay, so we have to convert both the integrand and the limits. So let's set up the integral as much as we can. So we can start. By setting up the integral, and we'll worry about the limits in a second. So you have double integral over r, negative x squared minus y squared plus 9 dA, right? And again, we're following our same strategy here as I said before. We should try to figure any x squared plus y squareds out first. So like negative x squared minus y squared, that's negative x squared plus y squared plus 9 dA, right? And so we'll use our x squared plus y squared equals 9. 9, why would it equal 9? Equals r squared. And then also, we may as well put in the dA, which was r dr d theta, right? So we'll do that. So our integral will become double integral over r. We've got negative r squared plus 9, and then r dr d theta, r dr d theta. So the actual integral is not that hard to set up. Now we have to worry about the region. Now let's look at r. So we've got the inequality here. So this was our inequality, and this should be really obvious what to do, right? Again, we're simply going to use x squared plus y squared equals r squared. And so this is really quickly just going to become, in between 3 and 7, right? So r squared is in between 3 and 7. So that's going to tell you that r itself is in between square root 3, square root 7. Get a square root. Okay, so that's easy. Now, what about theta? So remember what we did, not last time, but a couple times ago. If there are no restrictions on theta, then theta is just going to be all the way around the circle, 0 to 2 pi. Since we had no restrictions, theta between 0 and 2 pi. Okay, so what's our integral look like then? So our integral, r is going to go from square root 3 to square root 7. Theta is going to go 0 to 2 pi. Our integrand is right here. You can multiply that r in if you want. It doesn't really matter at this point. 9 minus r squared r dr d theta. If you want to, you can distribute if you want. You would if you were actually going to do the integral, but we're not going to do the integral because I feel like this was still not a tricky enough integral to waste our time on. But I wanted to set it up because it was a little bit new. We translated x's into y's in an integral this time. X's into y's. We translated x's and y's into polar coordinates. Um, okay. Oh, yeah. Excellent. We have one to actually do now. So we're going to solve this one. Translate into polar and evaluate. 0 to 1. Negative 1 minus x squared. Positive 1 minus x squared. 5 cosine x squared plus y squared dy dx. Okay, so the hard part of this, which is not hard, it's only hard the first time, is going to be understanding the region. Okay, so we need to understand the region D or R or whatever they're calling it. Okay, so what we've got listed here, this is in X's and Y's, right? So we've got Y between two things, and then we have X between two things. So which one's which? So our first integral is Y, right? So our first integral is Y, so Y is between these two functions. On the top, 1 minus x squared, and on the bottom, negative 1 minus x squared. And then x is just between 0 and 1. Okay, so you need to understand what the graph looks like here. And I'll do it on Desmos in a second, but what does y equals 1 minus x squared and y equals negative 1 minus x squared look like? And the answer is, well, they're circles, but let's look. So let's go Desmos here. Make big. Okay. Graphing calculator. So if you do y less than square root 1 minus x squared, you get that. Also, you can come to the other side and you can do negative. I should have done this one, but I didn't. Negative square root 1 minus x squared less than or equal to. I got the square, I got that in the wrong place. Okay, there. So if you go to plot this, of course, it's inside of a circle with radius 1. Okay, so that's the region that we're looking at. But then they also say that, how do I get the other symbols? Okay, yeah, there. They also say that 0 is supposed to be less than x, which is less than 1. So you can actually plot this entire, can't, okay, that's how. So you can actually plot this entire region by typing it there into Desmos, and you get the entire half circle here. It was 0 to 1 for x, right? Yeah. So like I just literally typed that in. You just have to know how to type in the 0 less than x less than 1 part. That has to be in curly braces after you type in the first intervals. So this is the region. It's a half a circle. Okay. Answer circles or half circles. The way you can see that, by the way, if you don't know that that's a circle, is if you square both sides, you get y squared equals 1 minus x squared. And then if you move the x squared over, it's x squared plus y squared equals 1. And that's the same thing that happens for both of these. They're both the same circle, x squared plus y squared equals 1. This is the top half and this is the bottom half. But we graphed it on Desmos, which is another nice way to do it. And what we saw was that the domain is this. Okay, so that's the domain. The x values go between 0 and 1. That's why it's only half the circle. All right, so the domain in terms of in terms of r and theta, what is it? It's r is going to be between 0 and 1, right? Because this is still r equals 1. And the theta, though, what's the theta? Well, same as the previous problem, I think, right? We want to go from there to there. So that's negative pi over 2 to positive pi over 2 for that half of the circle. Okay, so that's the first thing, is understanding that domain, because then you can set up your integral and your r can go from 0 to 1 and your theta can go from negative pi over 2 to positive pi over 2. And then you've got your function, 5 cosine x squared. That's simple enough that I don't really need to do this in a separate step, right? What's x squared plus y squared? R squared, right? So I'm just going to put an r squared right there. So we're simply going to get 5 cosine r squared, like that. And then what about the other part? What about this? Right? Hopefully we understand that that's dA, so it's going to be r dr d theta. Hard part is remembering this extra r. All right, so this is the integral. So once we've translated it, now we can solve it. Now, one thing I do want to say, like, we're definitely going to do this. It's like a super tough integral or anything. But I don't know off the top of my head how to type in a double integral into Wolfram, but I know I can do this. I can go integrate 5 cosine r squared r dr, right? I can just skip the d theta. I can go from 0 to 1 like that. And so the result you get is 5 sine 1 over 2. And then I can go 5 sine 1 over 2 from theta, I guess. I'll do t. T equals negative pi over 2 to t equals pi over 2. And so a lot of times I'll use t instead of theta because I don't want to, like, how do you type theta in? And for an integral, it doesn't matter what the variable is. So so the answer there is 5 halves pi sine 1. I'm going to check if that's correct. It should be. It is. Hooray. So you see I had to do that in 2 steps. I did the inside integral first, and then I just did the outside integral second. But it is possible to do on a computer. And there are like special double integral calculators that you could use as well. But we'll do it by hand. So to do this by hand, we would do a u sub. Use u substitution. So u would have to be r squared. And du would be 2r dr, which would mean that du over 2 would be r dr, like that. So I've got my integral theta goes from negative pi over 2 to positive pi over 2. We're just ignoring that for now. I've got my integral here. I'm just going to leave it like that for the moment. I got 5 cosine u, and then my RDR, right? I got RDR right there, which is RDR right there, is du over 2, like that. And then I got my d theta. So I do my u substitution there. Now, what about my limits, right? I like to translate my limits. So my top limit was previously r equals 1. So this is the limits. My previous top limit was r equals 1. Plug r equals 1 into the u equation, and you get u equals 1 squared, which is 1. So u equals 1. And then your bottom limit was 0. So what about r equals 0? What happened? Well, u would be 0 squared, which is also 0. So u equals 0. So if I use these, then I don't have to translate back to the original variable. So let's just take the 5 halves out of the entire thing. Negative pi over 2 to positive pi over 2. And let's do this integral. So we're going to go from 0 to 1. And we need the antiderivative. So I took the 5 halves out already. It's over here. So I'm just doing the antiderivative of cosine u du. So antiderivative is sine u. And then we got the d theta on the outside. So we just did antiderivative of that, basically, to get that. All right. So 5 halves, theta goes from negative pi over 2 to pi over 2. By the way, I haven't mentioned this, but the convention for writing the variable like theta here is basically just this. If you want it written there because it helps you keep track of it, then write it there. Otherwise, you don't need it. But you just have to remember what variable is what. Okay. Anyway, let's put the 1 and the sign and the 0 in. Sine theta, sine 0, d theta. Now, sine 0 is 0, so this is just sine 1 d theta. So sine 1 is just a constant. So we have 5 halves, and then the antiderivative of sine 1 d theta is sine 1 theta from negative pi over 2 to positive pi over 2. And so you get 5 halves sine 1. I'm just going to take the sine 1 out, and we'll put in the pi over 2 minus pi over 2, which is pi. So you have 5 halves sine 1 pi. And that is your answer. Okay. So this still wasn't quite what I wanted because we didn't really have a general region here. We're an hour and 28 minutes in, but I still feel like this is going better than previous. Too easy, too easy. Give me one that's not rectangular, polar rectangular, please. I guess I can just get one from the book. Let me pick a different question here, please. Oh, okay. So let's see here. No, it's still the same thing. Well, we can do one of these. So remember, the area of a region D is given by area equals the double integral over d of just dA. That's still true in polar coordinates. Okay, so here's a problem on this topic. So example, find the area of D bounded by the polar curve r equals 6 cosine 6 theta, where 4 pi over 3 is less than theta, which is less than 2 pi. Okay, so first of all, if you wanted to know what this looked like, we need to figure out some way to do that. And so we'll need to graph this if we wanted to have uh, some idea what it looks like. So we can try to do that in Desmos. I think Desmos can do polar graphs. If not, we could use Wolfram, although Wolfram is not interactive for graphing. So let's try Desmos first, graphing calculator. I think if I go in here, yeah, so like on the grid, you see, look, polar. Look at that. And then the curve is r equals, I don't have r, okay, no, that's rz. R equals 6 functions, cosine 6 variables. Where's the theta? Give me a theta. Where's theta? 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 How do I get a theta? I guess I'll use. How do I get a theta? I don't see it. Ah, there it is. Haha, I found you. Okay, that was too much work. All right, so 6 cosine 6 theta between 4 pi over 3 and 2 pi. So actually, that's a lot of pieces to this, right? Like, here, we'll copy paste it. We'll do this. Done. Save to photos. Well, I no back. I don't want the. I just want this. Okay. All right. So this is it. So we graphed that, right? And if you were going to talk about what the area is, right? So they said between 4 pi over 3 and 2 pi. So that's actually kind of a little bit of a weird area if you think about it, right? You have I did crop too much. I did crop too much. I believe this is 4 pi over 3. Oh, froze. The page is frozen. So I can go back. Then I go back in. Now it's not frozen. Okay. But now erase. Okay, sorry. I believe this is 4 pi over 3. And then, of course, 2 pi is, of course, over here. So what you're looking at then is you've got this section that's only half of that petal, this petal, this petal, this petal, there. Okay, so that's the area that they're talking about. And, that's fine. But, oh, actually, I lied because of the way it is. let me erase this. Sorry. I wasn't thinking. The way this gets traced was like you start here, right? And you go this way, and it goes through here. And so, like, this is the next one. And then here, and then here, and then here, then over here, and then over here, and then over here, and then over here, and then up here, and then over here, and then over here, and then over here. Um, yeah, did you get all that? Um, the point is if you actually look at the way it gets traced, it wasn't the ones that I labeled. It was this one, but half of this one. But instead of these two down here, because of the way, like right before it was doing this, it was actually doing this pedal. So like going backwards from 2 pi, it did this pedal, then this pedal, then this pedal, then this pedal, then this pedal. So what's labeled there is actually the area they're talking about. Now, the thing about it, though, is that as complicated as that seems, the region is actually pretty simple. Got this 2 pi down here. The region is actually pretty simple to write. So the region is r theta such that r is going to be between 0 and when they say bounded by this curve, that's the outside bound for r. So when they that's your bound for r. So that's right. That's why that's there. And then for the theta, of course, they gave you the theta directly, where they just said theta is between 4 pi over 3 and 2 pi. And so the point that I'm trying to make here is that you did not need to know exactly what this looked like. What you really needed to know was that, okay, well, if it's bounded by this curve on the outside, then r is going from 0 out to that curve. And then theta, well, they told you what to do for theta. So that's it. And then once you have that domain, then you know that the area is given by an integral. And so the area, which is the double integral over r of just dA, it's going to be double integral. The dA, of course, is r dr d theta. But then r goes from 0 out to that curve, 6 cosine 6 theta. And then your theta goes from 4 pi over 3 to 2 pi because they said so. So that was actually much easier to set up than you think. And that graphing it in Desmos was not strictly necessary. And then, of course, just solve it afterwards. So integral 4 pi over 3, 2 pi. All right, so this is the first one we've done with a not a constant up here, though. So you integrate r dr. What's the antiderivative of r dr? R squared over 2, right? And then that goes from 0 to 6 cosine 6 theta, and then d theta, like so. So then you plug those in, those limits of integration. Just hear weird sounds behind me. Weird when you're home alone. So put in the 6 cosine 6 theta. You have 6 cosine 6 theta squared over 2 minus 0 squared over 2 when you plug in your limits into here. D theta. I didn't forget my RDR, right? Okay, good. So of course, what we end up with here is 4 pi over 3 to 2 pi. You square this, you're going to get 36 cosine squared 6 theta over 2 d theta. You can take the 36 over 2 out as 18. 4 pi over 3 to 2 pi. Cosine squared 6 theta d theta. So you do all this, and then you have to say like, uh-oh, how are you going to do the integral of cosine squared 6 theta? And because it's trig functions, you just have to go to your trig identities. So if I'm going to look up the trig identity we need like, what's it called? Double angle or half angle? Something like that. Just, you can't see what I'm doing, but all of that was just me trying to open a web browser for a minute and failing. So trig identities, any page will work pretty much. There we go. Boom. We want the one for cosine squared. So you look up your trig identities. So specifically this one, cosine squared, 1/2 plus 1/2 cosine 2x. Okay. So we'll use our trig identity here. We have 18, 4 pi over 3 to 2 pi. That's going to be 1/2 plus 1/2 cosine. And so whatever the angle here is, it gets doubled. So if this is 6 theta, this actually comes up 12 theta d theta. This is fine. You can take out the half. They both have a half and make this 9 integral 4 pi over 3 to 2 pi 1 plus cosine 12 theta. If you choose, I guess I did because I did. Now let's do this integral. So okay, I see what they did. So let's do this integral. So antiderivative of 1 d theta is theta. Antiderivative of cosine 12 theta. You don't really need substitution, although you could use it, right? Remember, the 12 is just going to make you divide by 12. And then we go 4 pi over 3 to 2 pi. So put in your 2 pi plus sine, that's going to be 24 pi when you plug that in for 12 minus 4 pi over 3 plus sine. Okay, do this in our heads. We can do it. 12 times 4 pi. 12 times 4 is 48. 48 over 3 is 16. 16 pi over 12. Okay. So here's the thing. Any multiple of pi, like sine of pi is 0, sine 2 pi 0, sine 3 pi 0, etc., right? They're all 0. So this is going to be 2 pi. I lost 9. Let's get the 9. 9. So you have 9 times 2 pi minus 4 pi over 3 because all your signs there were 0. So 2 pi minus 4/3 pi is going to be 2/3 pi. So it's 9 times 2 pi over 3, right? Which is 18 pi over 3, which is 6 pi, I believe. Okay. And the result is, so the area we shaded on that graph is 6 pi unit squared. Okay, so you can calculate an area with a double integral, and having a limit of integration as a function doesn't really cause you any issues. It's the same as what you did in the previous section. Okay. Do one more of these. Maybe I'll just set up the integral. I don't know. Find the area inside the circle r equals 8 sine theta and outside r equals 4. Okay, now again, you don't need to know what this looks like. Well, you do actually. I was going to say you don't need to know what this looks like to do the integral, or to do the problem, but you do. You do. So again, this is where you would want to use a graphing tool to help you here. So when they say inside the circle and outside the other circle, like, right, R is going to be, you put the inside one here, sorry, you put the outside one here, the outside one there, and then you put the inside one here. So R is supposed to be between inside 8 sine theta and outside R equals 4. And so if you're trying to understand what that region looks like, then wait, why did I close that? That was dumb. It's going to be all laggy now. It is all laggy. So you want to, understand what that region looks like. And the reason you want to understand what the region looks like is because you need to figure out what your bounds are for theta, and we don't really know them right now. So we will switch over to polar again, and we got to do 4 less than or equal to r, which is, we'll figure it out in a minute, which is less than or equal to, we need a function, actually 8 times the sine of theta. Just sine theta? Yeah, okay, let's find the theta with there. No, it was, wait, it was there, right? It's there? No. How did I do this before? Shift? Oh, it's right there, okay. Oh, blind. Double inequalities of x and for y. Okay. So you have that circle. We can do it ourselves. So well, if I could draw. Okay. So 8 sine theta is, if you see, out to a radius of 8, right? You see the 5, right? So out to a radius of 8 here. And then it's just a circle like that. There. Now, you also need r equals 4. That's another circle, but r equals 4 is centered at the origin. Okay, so right, so this is r equals 4 right here. Now the problem is that, so this is the circle r equals 8 sine theta. So this is the picture, but it's supposed to be outside of, this one, but inside of this one. So the area that they want is this area. And so in order to do this, the tricky part is you got to figure out what thetas you have to use. So what about theta? Okay, so theta is in between two values here. Let's say I'll call them alpha and beta because they do. You have to figure out this theta, and you got to figure out this theta. And so that way, basically, you need those intersection points in order to set up this integral. Okay, so in order to do that, you have to figure out the intersection points. So where r equals 4 and r equals 8 sine theta intersect. It's not that hard. Just set them equal to each other. So 4 equals 8 sine theta, and solve for theta. So divide both sides by 8, you have 1/2 equals sine theta. So where does theta, sine theta equal 1/2, right? You end up with theta equals pi over 6. So this is going to be pi over 6. And then the one over here must be 5 pi over 6 because it's symmetric. And, you could get that another way, but that's how you do it. So the interval theta between pi over 6 and 5 pi over 6. So that kind of thing is kind of like one of the harder things you have to do in the section. But then actually setting up the integral is not that hard because your domain then is r theta. We just found out that theta is between pi over 6, 5 pi over 6, and we knew that the r is between 4 and 8 sine theta. That was essentially given, right? So our area is the double integral over the domain of dA. So for us, that's the integral from theta goes from pi over 6 to 5 pi over 6. R goes from 4 to 8 sine theta of r dr d theta. And so this is very similar to the previous problem at this point once you can write this down, right? So you're just going to solve this. Antiderivative of RDR is r squared over 2. Then d theta outside. That goes from 4 to 8 sine theta. So that's going to be 8 sine theta squared over 2 minus, putting in the 4 squared over 2. Not 0 this time. Okay. So this is going to be 8 squared is 64. 64 over 2 is 32. So 32 sine squared theta minus 4 squared is 16 over 2 is 8 d theta. Like this. What are we going to do to that sine squared, do you think? We are going to use an identity. I think we have a different choice for what identity we might use. Since I typed in different way. Come on, good identities. Let's see here. So we got sine squared. You could use, no, I mean, it's the same. It's the same one we used, but with a minus sign, right? Where is it though? Do you see it? Give me it. Life is hard. What I get, I should have just typed in trig identity and go back to the same page I was on last time, because the one that I was on last time, we found it right away. All right, there we go. The same one as before, but this time with a minus. That's what I wanted. So integral pi over 6, 5 pi over 6, 32, and then we're going to use times 1/2 1 minus cosine 2x, which in this case is going to be 2 theta, and then minus 8 d theta. So I did that the way I did it, so I could do the 32 times 1/2 and get 16 right away. But actually, now that I do that, I want to just multiply that out. So 16, so that was a waste. So this is 16. 16 times 1 is 16. 16 times cosine 2 theta is 16 cosine 2 theta. Then, of course, minus 8. And the reason I want to do that is because 16 minus 8 is 8. So I wanted to combine these. So we have 8 minus 16 cosine 2 theta. All right. Great. So integrate. 8 theta minus antiderivative of 16 cosine 2 theta is going to be 16 sine 2 theta over 2. Pi over 6 to 5 pi over 6. So we get 8 5 pi over 6 minus 8, because 16 over 2 is 8, sine 10 pi over 6, right, because we're multiplying by 2, minus 8 pi over 6 minus 8 sine 2 pi over 6, which is, I'll just write pi over 3. All right, so let's do these. So we have 8 times 5 pi over 6, that's 40 pi over 6, minus sine, I'm going to do this on the calculator because I'm lazy and my brain is bad. So 10 pi over 6, of course, it's 5/3 pi, but sine 10 pi over 6, negative root 3 over 2 times 8. That'll make it a plus 8 root 3 over 2. And then you've got minus, we're going to distribute the minus. 8 over 6 is 4/3. So 4/3 pi. Like so. And then minus and minus will be a plus. And then sine of pi over 3. Well, what's sine pi over 3? Root 3 over 2. So 8 root 3 over 2. So overall, what you end up here is you've got 8 root 3 over 2 and 8 root 3 over 2. So that's actually 4 root 3 and 4 root 3. That adds up to 8 root 3. And then you got, this is 20 pi over 6. Sorry, 20 pi over 3 minus 4. So 20 over 3 pi minus 4 over 3 pi is going to be 16 over 3 pi. And it was an area, so I'm going to write units squared. Okay, those were fun, right? Okay, that's another 2-hour lecture there, but I think this one was easier. I think just this lecture takes a long time because the integrals are long. But I did one of basically everything here on the homework. So in fact, while I was doing the homework, I think I got the homework up, or while I was doing these problems, I think I got it up to 90%. I did skip a couple, but I did most of them. Okay, so that's it. I will see you next time. Good luck on this homework. You're good at integrals now, right? So this will be easy for you.